Good morning, good afternoon, good evening, wherever you are on this planet, planet Earth, and welcome to our SETI Live. My name is Franck Marchis. I'm a researcher, director of the Citizen Science at SETI Institute, and today I'm going to talk about exoplanet and Earth as an exoplanet. And because I don't do this kind of research, we invited a researcher that's going to tell us more about this. Hi, Björn, how are you?
Great. Thank you for inviting me and having me here. It's a pleasure to talk to you.
Nice having you today. So Björn is doing a PhD in astrophysics at ETH Zurich, where he studied the atmosphere of distant Earth-like planets. And he dedicated his work mostly on the study of I can predict weather, atmospheric makeup of these exoplanets. But today we are going to specifically talk about the Test Earth experiment, which has been developed for a space mission called LIFE. LIFE means Large Interferometer for Exoplanets. And this is a telescope project. It will be basically a telescope that could detect signs of life on planets orbiting distant stars. Okay, it's early for me in the morning, so I hope our audience will be okay with that. I'm in New Orleans right now because I'm on my way to go to see the eclipse Monday in Austin. And tell us where you're watching us from. And in the meantime, Björn, I'm kind of confused. What is this Test Earth experiment of things that you mentioned? Are you telling me that you find an hiding civilization of our own planet, some kind of mole aliens living underneath the planet? What is that?
Well, the test Earth is just we look at Earth, and unfortunately, we do not find anything surprising. But I argue this is sort of expected because an intelligent civilization would probably hide itself from humans, given our history of dealing with other civilizations. So okay. I'm not surprised that we don't find any secret civilization yet, at least.
Okay, so the Test Earth is an experiment for the LIFE, in anticipation for the LIFE telescope, the LIFE space telescope. So tell us, what is LIFE?
So the LIFE telescope is sort of an idea for a future telescope, which will come after the current James Webb telescope. Because what the James Webb telescope can't really do is look at a planet like Earth around the star and look at its atmosphere. That's not really possible with James Webb. So we need a next generation of telescopes to do this.
And so this telescope, what does it look like compared to James Webb Space Telescope?
Well, I would say the main difference is that it is no longer one single telescope, but it will be basically 4 mirrors that collect light and one additional spacecraft, which is called the collector spacecraft, where the light from all the 4 mirrors is collected and combined and then analyzed. And the reason why we need this interferometer is just basically an interferometer is the same thing as a really, really big telescope, but you don't need to build a really big telescope, but you can place the mirrors very far apart, and the resolution of such an interferometer will be the same as a really big telescope. So that's why we need an interferometer.
You're creating a virtual telescope, basically,
exactly, more or less,
in space. And we have done that before. That's something new. What's the...
Well, on Earth, on the surface of Earth, we have done it. But in space, to my knowledge, this hasn't really been done before. So this is sort of the next step. And the other big thing about LIFE is that it will measure the mid-infrared light, so the heat coming from the exoplanet. And that is also, James Webb can do this, but not for an Earth-like planet. Yeah.
We're gonna go through this in a few seconds. But before, let me say hi to people. So since we're doing this SETI live at different time that normally we have people from joining us mostly from places that, mostly in Europe. We have Texas too, of course. Just when I look, there is someone who contradict me. Thank you, guys. Manila in the Philippines, New Jersey, Germany, Greece, Uranus. That's not possible, dude. Come on. Well, you say hi, but you don't say where you're from. So Western Australia, thank you. Denmark, London, Essex, UK, Arkansas, Italy, and more people will join us as we talk. Okay, so we have a virtual telescope called Life. It's an interferometer. It's something on paper at the moment. Yes. And as usual, when you want to push for a project like this, which is going to be expensive, obviously, you have to simulations, experiment, showing that the capability of this telescope. Okay, so tell us what you did, what this TESS Earth experiment is all about.
Exactly. So currently we have to define what life needs to look like. We need to know how big it needs to be and how good the instruments on life need to be. And since we want to look at Earth-like exoplanets, it is sort of the first step is to look at Earth itself and look how Earth would look if we could observe it with life, and then analyze the data that we would get from Earth if we pointed life at Earth. And so that's what we do in this study. We just take an Earth spectrum and look how it would look like through life, and then analyze this spectrum, try to characterize Earth's atmosphere from this very limited data.
All right. So you use what spectra of Earth did you use? I mean, do you use a real observation? Do you use simulation? How did you feed your model?
We use real observations from satellites that are orbiting Earth and constantly measuring Earth's spectrum. And so the spectrum we get is sort of an average spectrum of Earth. So it sort of blends all the continents and stuff like that and gives us the average expected spectrum of Earth.
And that's nice. So, and what do you look exactly for in terms of biosignature? Let's talk about that specifically. Maybe you can explain what biosignature is and what have you been looking at specifically?
So a biosignature is basically just any signature in the spectrum which is caused by life on Earth. And the biosignature we mainly focus on in the mid-infrared or in the infrared spectrum is the presence of different gases in the atmosphere. And the most interesting one, and the one we focused on, was the presence of methane. So the greenhouse gas that is produced by cows and bacteria on Earth, and is then put into the atmosphere, and we try to detect gases like that in Earth's spectrum.
So methane, what kind of?
Methane, oxygen is an example, although oxygen doesn't have features in the mid-infrared, but another molecule in Earth's atmosphere is ozone, which is produced from the oxygen, which is very easily detectable in the mid-infrared. So that's also a potential biosignature. And then we can also look for other important substances which are not biosignatures, but are important for life. For example, water, or we can also look for CO2, which is an important factor when it comes to maintaining a stable temperature on Earth as a greenhouse gas. That's also a gas we can look for.
And because you're observing in the mid-infrared, you can also have an idea of the temperature of the surface of the planet, right?
Exactly.
So that's a very important parameter, because if the temperature is between 0 and 100 Celsius, you will basically you can claim that you could have liquid water on the surface.
Exactly. That's also one thing that we can easily constrain in the mid-infrared if there is not a very strong cloud cover like we have, for example, on Venus, because there the clouds cover up the surface. But on Earth, we do get quite a good estimate of the surface temperature and also the surface pressure. And this already tells us a lot about the planet.
So what data will you get with life? An image of Earth, a tiny dot? What exactly, what the data will look like?
So what we will get from life, so Earth will just look like a dot. Okay. 1 pixel on a screen. Okay, it's maybe spread out a bit because of the optics, but basically it will be a dot. You won't see continents or anything. But what we get is we can look at the color of this dot. So maybe you know the album cover of Pink Floyd, Dark Side of the Moon. We can basically split up this light that we get into different components, the different colors. And this doesn't only work for optical light, but this also works in the infrared as well.
Okay, before we dig more into this, I want to say hi to people who join us from Pridnetstrovi in Moldova. Sorry for the pronunciation. We have someone from Peru, New Jersey, Illinois, Moa, Kansas, and yeah, thank you for joining us. So we are talking with Björn Konrad about the LIFE telescope. It's a project telescope, but also his experiment that he published recently with other people in Astrophysical Journal. The paper, led by Jean-Noël Mettler, is entitled Using Empirical Thermal Emission Spectra as an Input for Atmospheric Retrieval of an Earth Twin Exoplanet. We will post on the chat the link to the paper if you want to have a look, if you are curious to see the science behind this conversation. So, so you mentioned Earth will be a tiny, if you observe something like Earth, an Earth twin from far away, what's the distance basically you have, you made these assumptions?
So for the distance, we assumed objects that are sort of within 10 parsec from the Earth. So that's about 30 light years.
30 light years.
On a galactic scale, extremely close to Earth. But the point there is, from these objects, we get enough light to actually measure a spectrum of such a planet.
Yeah, there is a sweet spot between being close. If you close, you're bright enough to be able to see to get some photons coming from this planet. Basically, that's the reason
that's one
you are limited to 30 light years, roughly.
Exactly.
Okay, so that would be a tiny dot. I mentioned that, a speckle, which I love because I do adaptive optics, and we always observe planets, and they're a tiny dot, and they're moving, and I think it's exciting. But only astronomers will think that is exciting. But anyway, then there is a bit of complexity here. I'm sorry to go through the details, but the emission that you see will depend of the size of the planet, of the orientation. What else? There is plenty of parameters that could make this light, the brightness of this dot change over time, like seasonal fluctuation, the presence of continents, all of this. Can life detect this, and can you disentangle between all of those phenomena? Did you run this into your simulations?
That's sort of one thing that motivated this publication. So in the publication, we really look at different views of Earth, so different orientations of Earth relative to us. So whether we see Earth from the North Pole, from the South Pole, or centered on the equator, and then also different seasons. And what we see is that for a lot of parameters, these fluctuations in Earth's spectrum are too small to affect our characterization. The only parameter that is really significantly impacted by this view is the temperature that we measure. And so we are sort of sensitive to temperature fluctuations between summer and winter for the northern hemisphere. But other than that, like the detectability of gases in the atmosphere and other parameters are not significantly affected. So that's one of the major points we try to make in this publication.
Yeah, and I glanced through the publication. I mean, there is a lot of analyses which are way more too advanced to explain here, like Bayesian analysis and so on. So if you really want to know more details about that, I recommend you check the paper. and you see the different scenario, the different type of simulation. And in fact, this paper is part of a series of papers, Earth as an exoplanet. There is already, how many of them have been published?
This was the third one. Yes.
The third one. And there will be probably more coming, I'm assuming, right? Because you need to finish this PhD.
Exactly.
All right. Okay, so you have published already like 3 papers, and there is more research working. So how this simulation influence basically the design and the development of instruments for the life mission?
So what we do in this work is we test different setups of the life mission. So we basically check how does our characterization depend on the size of the telescope, the resolution of the spectrum we measure, so how many data points we get, and also how accurately we measure them, so the error bars on the spectrum basically. And we test various different cases and try to identify where is the sweet spot, because of course, if we want to get better spectra, it will be a lot more expensive, and bad spectra is just not good enough. So we try to identify where the sweet spot is, and this will then give us first constraints on what we need for the life mission. So how good the instruments need to be. And this is really the idea of this work.
Okay, that's interesting. I mean, that's how we did instruments in on the ground too. When we develop adaptive optics for exoplanet search like GPI, that's what we have been doing as well. It's doing simulations and refining the wavelength we observe, the resolution as well, etc. But this is in space, and this is significantly more expensive. I mean, what's the idea? Would you have an idea of the budget of the life mission? What will be it will cost to launch something like that?
We don't really know yet, but it will be about the same amount as James Webb or similar missions, if not, around that range. But we are currently working on getting these first estimates. Good.
Okay, we're gonna take some questions. I'm sorry, my headset just stopped working, so I hope it's still working now. Could we detect intelligent life on Earth using if we were just 10 light years away with our current technology?
Well, current technology, I mean, if you detect radio signals or something like that, maybe. With life, we think it will be possible. There is a paper on detecting technosignatures with life. So basically gases in the atmosphere that are produced by our industry, like CFCs and other gases like that. And there is a paper on that in the Life paper series. So we are also looking into this. So I believe it should be possible.
Okay. If we can launch Life, when will it be launched and then in operation? The earliest?
Currently, we're trying to do it before 2050, but it's still a very long timeline. We're basically at the point where James Webb was 20 years ago, okay, or 25 years ago. So yeah.
So people are introduced. To all my viewers, I introduce you Björn Konrad. He's going to be the director of the Life telescope in 20 years. Because I will not be around, you will be around. You will be the one. Remember this video. Okay. What do you say intelligent aliens will be hiding from us? Are we hiding from them? So that's mostly for me. That was a joke, guys. That was we are not going to talk about aliens hiding from us right now. We are talking about searching for potential Earth twin exoplanets using an instrument called Life. Okay, dude, that's a real name apparently. Is spectroscopy useful for detecting biotechnosignatures on a body without atmosphere?
Well, to some extent, yes. There are also so-called surface biosignatures, like one thing is, okay, then the question comes to, could we have planets without an atmosphere? But on Earth, there's the so-called vegetation red edge, which is sort of a spectral feature that is caused by reflections of sunlight by plants. The other thing is, maybe on an icy moon or something, I guess it would be a lot harder, where you basically only have subsurface life. I guess in that case, the possibilities of spectroscopy would be limited, at least with an instrument like LIFE.
Okay, thank you. Another question. If we guess there are 2,500 stars within 30 light years, how many of these could be potentially interesting or habitable or Earth-like or whatever? Do you have an idea?
Well, that's a great question. I don't think anyone knows the answer. I think it really, one big question that will be solved with James Webb is if planets around small stars, like the TRAPPIST system, if these planets can have an atmosphere. And if we find an answer to this question, this will already give us a lot of information about this, because the most abundant star close to us are M dwarfs, so very small, faint stars. And if these planets can't have an atmosphere, this already constrains the number of interesting stars a lot.
Yeah. Hey. How did you start working as a PhD student on this project? Was that something you chose? Was it what happened? What's the story behind this, your involvement in this TESS Earth and the LIFE mission?
Well, I studied at ETH, and my professor, Sasha Quantz, I did a master's thesis in his group, and then he basically offered me a PhD thesis. So I already was involved in the LIFE mission in these sort of characterization studies in my master's thesis, and then just continued on the same project for my PhD.
All right. How many years of PhD you have more before you finish?
I hope I can finish this year. Yeah.
Okay. Oh yeah. It's the end of the light at the end of the tunnel then.
Yes.
Okay. Good.
One could say that.
Yeah. It's it's a great topic for a PhD. I'm assuming you like doing simulations more than instrumentation. You're more the simulation guys, right?
Yes, I'm more of the simulation guy, and we have a whole team of people working on the instrument and demonstrating the technology needed in the lab at the moment. So that's the other big part of the LIFE initiative right now.
Okay. So ETH is leading this effort. Who else is involved in this LIFE mission project?
Basically, a lot of other institutes right now. So it's mainly a thing that's concentrated on universities right now. Mm-hmm. So a lot of different groups at different universities are involved, and we sort of are trying to get ESA involved right now as sort of for the LIFE mission to be a complementary mission to the Habitable Worlds Observatory that is pursued by NASA at the moment. So then we have 2 future exoplanet missions trying to characterize Earth-like exoplanets.
Good. Okay, so that was going to be my last question, but we kind of infer already this question. You are a young researcher. You mentioned that these mission, LIFE and others like Habitable World Observatory will be in operation in 20, 30 years. So what do you think will be the impact on our civilization, our society, if one day you team, imagine the future Björn, find life or find a signature of life on an exoplanet like Earth, not too far away from us?
I think there's 2 big implications of that. One is sort of the obvious one. It will be the next or another big paradigm shift in how we see ourselves, right? From the geocentric view to the heliocentric view to the realization that we're just one star in a huge galaxy And the next shift was, okay, there's millions, billions of galaxies out there. And now, if we find life somewhere else on an exoplanet, the last thing we have, which is sort of special, is also proven to be abundant in the universe. And the second one is maybe more my hope, that the realization that life also exists on other planets will bring us as humans closer together. That we don't have sort of these conflicts between nations anymore, but we see ourselves as humans or Earthlings rather than, I don't know, Europeans and Americans.
Thank you.
My
That's a very good answer. I like the two sides of the answer because that's also something I say often. So thank you, Björn, for joining us and telling us about life, the Test Earth experiment. And I have the feeling that we're gonna have you more in the future on our SETI Live. There is some kind of good kind of connection between your research and what we are interested in at the SETI Institute and all our viewers. So thank you again.
Thank you very
much. And good luck with you last year of PhD. Because that I know this is a tough one, always. I'm still traumatized. Okay. Well, to all our viewers, that was a SETI Live with that was a SETI Lab, sorry, with about the life mission. We are the SETI Institute. We are a non-profit organization. You can support us by liking this video, sharing it, commenting it. We read our comments. We answer to some of them when we have a time or when we know the answer, of course. You can support us as well by just simply receiving our newsletter called Journey. And if you are inclined, if you want to support this research and this outreach specifically, you can make a donation. Go to SETI.org, click donate, and and follow the instruction. And you can send us 5, 10, 1 million pesos, dollar, whatever you want, even Bitcoin if you want. We receive Bitcoin now. All right. Thank you again. And it was great having you again, Konrad and Björn, sorry. And we see each other next week. I don't remember what will be the SETI Live next week, but it's going to be as interesting as this one. In the meantime, in my case, I'm going to pack my stuff and try to find a place where I can watch the eclipse, the total eclipse, nearby Austin. Hopefully the weather will cooperate. Right now, it's not very good, but we astronomers, we're used to that. I remember traveling for like 14 hours all the way to Chile to do an observation of a very specific phenomena, a conjunction between a transit between satellite of Jupiter and arriving there, and it's snowing. So I'm used to it. It's part of the game of being a ground-based astronomer. Anyway, we're gonna have a SETI Live Monday, so watch it if you want. You're gonna hear a lot of astronomers who are distributed along the path of totality of the eclipse in the US and in Canada. And hopefully we will show you the eclipse using the unistellar telescope. So you can, if you are not on the path of totality, you will be able to see and to enjoy an eclipse through our stream. Thanks again. You take care and see you next week or in 2 weeks, on Monday in my case. Bye-bye.